Okay, so now we know the definition of an inner product or scalar product, and we have seen quite a few examples of these. And as again, you can keep in mind as your basic example, the one you can refer to when you are trying to understand some new concept, it's the usual dot product in Rn. Okay. So let's do what we said we were aiming for. We were aiming for defining distances first. So to define distance, we are going to define norms. All right. And more exactly, the Euclidean norm, because, well, there are a lot of ways to define a norm, but the Euclidean norm is going to be the one that comes from an inner product. All right. So the Euclidean norm on a vector space E, when you have a well-defined inner product, it's just going to be given as usual, as the norm of x is the square root of the inner product of x with itself. The norm of x is the square root of uh, inner product of x with itself. Okay, just like you would do in Rn, right? So in Rn, if you've got x that is defined by its n components, you know that the dot product, well, if we define the inner product as being the dot product of x with itself, you know that it's going to be the sum of xi square, and so the norm of x is the square root of the sum of the xi square. Okay, well, you already know about this, at least in dimensions 2 and 3. Okay, and so now the distance between two vectors, two items of our vector space, is just going to be the norm of x minus y. Okay, that's so that if you are working on spaces of functions, as we saw some examples previously, you can define the distance between two functions. Okay, using, for instance, that when we were working in C0 of AB, we had defined these products by saying that f product with g would be the integral between a and b of f of t times g of t dt. So that's a very common inner product defined on continuous functions when we're looking at a finite a bounded interval. And so that's it. And so if you, the norm of f would be given by the square root of the integral between a and b of f square of t dt, and the distance between two functions f and g, well, let's take the square so that we don't have to take the square root. That would be the integral between a and b of f of t minus g of t square dt. Okay, so, and again, if you take the example with the matrices, you can define the distance between two matrices with respect to this inner product. Okay, the inner product we had defined with a trace. Okay, a few properties, remarkable identities. So, well, basically, these ones are just going to be working on the expression. So let's have a look at the first one, for instance. If I'm looking at x plus y squared, okay, by definition, that's x plus y, scalar product, inner product with x plus y. And now I'm just going to expand that using the properties of the inner product. So I'm using linearity. That's x plus y, plus y, x plus y. I have used here linearity with respect to the first input. Then I'm going to use linearity with respect to the second input. So that's going to be x plus x, y plus, so that was for the first brackets, second brackets, that's giving me y, x plus y. Okay, nice. So I can already say that x with x is going to be x squared, y plus y, y with y is going to be y squared, and using the fact that this inner product is symmetric, these two elements here, they are actually the same, right? So I can write 2 times xy because this is also equal to yx. So that was for that one. Okay, and actually you can do all the other ones by doing exactly the same steps, all right? So this one, what you will get a minus here in that place. This one, um, for that one, for the fourth one, the third one actually, you just have to do the sum of the two previous ones, and this one comes from the previous one. You can rearrange, find this one by rearranging the previous identities. Okay, so you don't have to remember these actually. You don't have to remember these. They may come useful doing some calculations, but the thing is that you can most of the time you will be able to work that out. Okay, but practice the proof of these properties. It's a nice way to practice the main properties, linearity and symmetricity of the scalar product.